Okay, well, I guess we'll get started. So you're all very welcome on this very muggy. I don't know where the rest of you are, but certainly in Dublin, it's quite a muggy evening. It's not particularly warm, but it's just kind of, a bit. But still, it could have been a lot. It was a lot worse. I was in the UK and Spain in the last month or so for the heat wave, so that was fun. I'm not really genetically disposed to that kind of heat. But anyway, so thank you very much for coming, everyone. This is kind of the Dublin Data Science Workshop series that we kind of run, which is much more practical, much more hands-on. We are back for our in-person events, though. We actually had one with our main organizer, Richie Morrisroe, which unfortunately I missed due to illness, which is also why this workshop got delayed a week. I'm fine now, though. I happened to be in England and I missed my flights and stuff and had to wait longer, all that kind of stuff, the usual mess, especially with traveling at the moment. So I missed it, unfortunately, but I heard it went down very well. And we will not have an in-person event probably in August. This was supposed to be, I know this is the 1st of August, this was supposed to be last week. We probably will do another one of these workshops, but it's possibility we'll do a workshop towards the end of August, but I think it's more likely we'll just leave the in-person until the middle of September, because typically the attendance in August is generally poor between holidays and going back to school and all the other usual ups and downs. So we'll probably just leave it with a workshop for August, and then we'll have probably a bunch of talks then September, October, November. I imagine we'll have a bunch of in-person events in the autumn. But anyway, we can press on. So thanks everyone for coming. So this is a workshop series on Bayesian statistics taught via customer lifetime value models. So the basic, I'll go through the usual spiel, but I've also been very conscious that the last couple of months and the workshops have been kind of pretty far apart. And I'll be very honest, I wasn't particularly happy with how the last workshop went. It was just a bit all over the place, and I wasn't particularly happy with how I explained some of the concepts. So what I'm going to do is we're going to take a step back for this workshop, and we're going to kind of recover most of the content that we've done with an idea to kind of, not very thoroughly, we'll just kind of give a fairly, I don't want to say a thorough, but we'll give a reasonably decent overview of everything we've covered. Just one sec, I'm just going to put on mute there, yeah. And basically cover the problem, what we're doing, why we're doing it, how Bayesian statistics kinds of works, and what the concepts are, and specifically then look at how these kind of models are broke down into different components, and then discuss the various Bayesian approaches to those components. And then we do have a couple of new parts that we haven't really covered yet in the workshop series. We'll hopefully get to that towards the end of this one. And with a view then to kind of combining them later and actually using external data, because right now we haven't actually really tried to fit any of the actual data set that we're using on. So the background to this kind of problem was in 2021, I gave a series for Dublin Data Science on data science soup to nuts. So the idea was it was kind of a full data science project from start to finish, covering data exploration and visualization, coming up with problems, all that kind of stuff. And as part of that, I was always intending to cover kind of customer lifetime value, and specifically these particular models, which we will talk in a few minutes, called buy till you die models. For various reasons, they weren't really, they were just a bit too much. They were a bit too complicated, a bit too, I don't want to say sophisticated, but there was a bit too much going on with them to really cover them in a decent detail as part of the workshop series last year. So I kind of decided to square a circle. I wanted to go back and redo kind of the Bayesian stuff, because that's generally the way I model, and I think it's a really powerful approach. But the problem with teaching Bayes is it tends to be taught via like these very toy problems that aren't particularly useful. And I wanted to give a real world example. And this kind of just seemed like a great way to kind of combine the two. Now, for those of you who haven't been at any of my talks before, I recognize a bunch of names. So hopefully most of you are. I'm more than happy to take feedback. And if you have any questions, sometimes unmuting can be a bit messy though. So I'd say the easiest thing to do is I have two screens here and I have the chat window up. So if you have any questions about what I'm doing, just pop them into the chat and I'll get to them when I can. I'll probably get to them as pretty quickly, unless it's something that I'm either about to cover in maybe 10 minutes time, or it's a bit of a tangent and then we can cover that maybe at the break or whatever. So that's kind of the rough flow. The workshop is 2 hours long, but we will take a break in the middle. It's almost it's just gone 7:05 here. So we'll take a break in or around the hour, depending on where we've got to and how people are doing. It'll be either like, anywhere from 7:45 to 8:10, depending on how we go, probably with a preference to a bit earlier. We'll take a 5-10 minute break, let people go to the bathroom, grab a cup of tea, get a drink, whatever they want to do. We'll come back then and we'll see it through till probably, depending on how we go, either 8:45, 9 o'clock. Just basically we'll see how we get on in terms of the questions, and if people want me to cover stuff again, by all means, do not be afraid to ask me to repeat myself. If I'm not explaining something well, or I say something random that you want me to go over, or something that's piqued your interest, please by all means ask me. I'm more than happy to kind of go even on slight tangents if it's relevant. So and also, to be brutally honest, speaking at a screen for 2 hours is very, very tiring. So getting feedback via the chat and stuff is really, really useful, because it kind of helps. It even helps me kind of, it just makes the whole thing a bit more interactive. Okay, so right, I guess let's just start and I'll get cracking. If anyone has any questions, like I said, please pop them into the chat. But yeah, failing that, we'll get started. So basically we have, like I said, I'm reusing the data that we use for the soup to nuts data set with a very different intent. So I should probably scroll up. So basically it's a set of transactional data. Let me just go right up to the top actually. This was kind of the data that was provided. So it was the transactions were from like 2009 to 2011. They were a bit weird. I think it was a brand new business that also took a lot of business online or something. And the transactions were very weird because there was returns. There was basically, the data was kind of messy. And I talked about that a lot more in the other workshop series. By all means, take a look at that. I talk about that extensively. But what we're going to do is kind of a very commonly used kind of set of models in the retail space. Well, I don't want to say common because I don't know enough about retail, but I certainly know of retail focused businesses that use these kinds of models. And I also know that some of these models are provided by default from, I think, Amazon and Google and a few of the others. If you put your kind of your transactions into their, BigQuery or Redshift or any of those kind of the big data storage stuff that the cloud providers provide, and you put it in a certain format, they automatically fit some of these models for you. So that suggests to me that these are reasonably well used, or at least commonly considered models that are used in this space. But like I said, I am no expert in retail. Retail is not my background at all, but I do find the models quite interesting. So this is the data that we have, and basically, I just, as I said, what we're trying to do is get a sense of from our clients, just try and get some quantitative information about them. Now, there's a whole bunch of different ways that customer lifetime value is considered. What we're looking at is a thing called the buy till you die models. So they're particularly useful in a non-contractual setting. So when you don't have like contractual touch points with your customer, so you're like, retail is a great example. They are not required to show up at any particular point in time, unlike say a subscription model where you pay a monthly fee or any of that. When it's basically, when there's a certain amount of or a large amount of discretion on behalf of the person, that's when these models are particularly commonly used. And I think that was the environment in which they were kind of considered. So basically what they do is they have, what we think about is, I'll just let me scroll down here. So this is kind of a visualization of the customers. So if the customer ID is here on the right, I'm assuming these graphics are large enough, by the way. If you need me to zoom in or anything like that, I mean, this is nice, I can get it all on one screen, but if there's anything in particular you need me to change, or there's something you can't hear me right, or the screen needs to be better, just let me know, please. Like, don't be shy. So this is kind of a representation of the transactions of the customer. So you can see that there's all these customer IDs which were assigned by the system, and then this is the date of the transaction. And this is just a quick visualization I came up with to kind of get a sense of different customer patterns. So I just randomly chose, I think it's 30 customers, and just drew a horizontal line. And you can see basically, you know, some customers started, what this customer 14225 kind of started in early 2010, transacted a couple of times, and then stopped transacting kind of late 2010. Okay, whereas this customer kind of 14113 has pretty much been transacting throughout the entire window that we've been observing, and so on and so forth. Okay, so this is kind of getting a sense. And what Buy Till You Die does is it makes a couple of like assumptions about this customer behavior. But the main thing what they're trying to do are, it's a version of what's called RFM modeling, which is very common in marketing. RFM means recency, frequency, and monetary. So you essentially try and categorize customer behavior in terms of their recency, which is basically how long since they last transacted. The frequency, which is a question of how many times do they transact? Is it like the count or per week or whatever it is? And then the monetary is when they transact, how much do they spend? And there's a bunch of different ways of doing this. So the way the Buy Till You Die model works is, and it's based on a guy called Peter Faber. There's a whole load of work online for it that talks about all these. And he basically makes a number of relatively simple assumptions, although they're simple assumptions, but they're actually quite strong assumptions, as in, you know, they're not necessarily, you know, they're a strong assumption in mathematics, as in it's, you know, it's quite strong. I'm not explaining this well, but like, it's not necessarily, in some cases, strong assumptions can be wrong, but they can also give you quite a lot of power. So they make the assumption that essentially a customer is, quote, born on the system, i.e. their first transaction occurs, that's when they are born to the system. They then transact for a certain amount of time, and then they die, and then they no longer transact anymore. And that's kind of the, and then they you know, and then so they essentially kind of have a lifetime, and they kind of have a frequency, and it doesn't, the Buy Till You Die models don't really focus on monetary, at least initially. They were focusing mainly on the recency and the frequency and the lifetime. So that's kind of what we model. And then the various Buy Till You Die models have different statistical assumptions around those concepts. So like, you'll have different concepts around exactly how the customer transacts, or how their lifetime is modeled, or how their frequency is modeled, and stuff like that. And, you know, there's a bunch of different models that fit within that general framework. But in general, what you're looking at is a statistical model for the lifetime, and then a statistical model for the transaction frequency. And then you bring those two together, and that gives you that particular variant of the Buy Till You Die model. Okay, so that's basically where we started. That's kind of our starting point. And there's a whole bunch of things we did on that. And this was from the workshop last year. I talked about this a lot earlier. But what I also want to introduce now is kind of the idea where, I mean, all of this is done and can be fit under, you know, maximum likelihood estimation. But I don't want to do any of that. What I want to do is talk the Bayesian approach to all this. So with the Bayesian approach, when you've got a statistical model, Bayesian statistics is slightly different. It's a different interpretation of how statistics works. So the idea behind it is that you have prior information, which is some kind of encapsulation of your existing knowledge about the world, and then you observe some data that you've observed, and you apply some kind of likelihood model. So you have some kind of, probabilistic formulation for how that data may have occurred. You combine the prior and the likelihood together to get what's called a posterior. And then essentially your statistical model, the outputs of your statistical model are these posterior distributions, which basically encapsulates everything that the model can say about what you're modeling, if that makes sense. So the whole point of Bayesian statistics is that you don't come up with point estimates for values. You're instead coming up with distributions of values. So rather than saying, for example, that a customer transaction frequency is once a week, instead what you would say is it's anywhere from 0.3 of transactions a week to 3 transactions a week. And you would have some kind of distributional form around that. Doesn't necessarily have to be analytical or some kind of closed form probability distribution, although typically you will use these kind of probability distributions as a way of kind of framing this, because essentially it means that the maths works out nice. So basically, that's essentially where we're going. Now, I talked a lot more about Bayes. For those of you who haven't seen Bayesian statistics at all, I mean, I have a couple of earlier workshops in this series that go into a bit more depth about how we think about it. But what we have done now is I want to kind of focus on a very simple, just modeling the transactional frequency, because it's probably the easiest thing to get our hands around. So we have a customer who transacts, and what we want to do is we want to have some sense of how frequently the customer transacts based on the observations of that customer that we have. Okay. Now, we are not using so far, we will towards the end of this workshop, but up to now, I haven't used the actual data that we got online. Instead, I've been using synthetic data for the simple fact that with the synthetic data, I can actually create data that by a model and then use the model in Bayesian statistics to try and recover the parameters. And while that sounds kind of stupid, as in like you're marking your own homework, the point of this is it's a great way of actually figuring out if your model is valid and if your model is correct, because it's actually surprising how often you will have some model for fitting your data, and then you produce data based on that model and then try to fit it back again using the same model, if you know what I mean, right? It's quite often the case that you're not able to properly recreate your inputs. So it's not a fully reversible process. And there's a couple of reasons why that can be. But a common one is like it's a great way of finding programming mistakes or errors in your logic. Sometimes actually the model itself the data you've observed is far too aggregated or censored or noisy or whatever to properly recover the parameters. And that's something that we will observe in these models, certainly on the lifetime side of things. So, it sounds kind of stupid, but it actually is really powerful. It's a really powerful technique that I think not enough people do. I found I've learned an awful lot from this exercise of just trying to if I'm trying to model some data, trying to figure out what is called the generative model that generated that data. So can I come up with some kind of probability distributions or combination of probability distributions that generates data that looks a bit like the data I'm trying to model? And you learn an awful lot about things by actually trying to do that. So that's kind of what we're going to do here. But has anyone got any questions? I'm very conscious. I know I'm kind of covering old ground here. But like I said, the last few months, I think have been a bit sketchy. And the last month I wasn't happy with it all. So for those of you who joined late, I'm kind of going to do a reasonably thorough kind of review of where we are before I try and move on, because I even managed to confuse myself last time. Quick drink of tea. Okay, so we've generated basically we've generated some data, some frequency data. So the idea is that we have a whole load of customers that were born around the same time on the same day, let's say at different hours of the same day. At birth, they're assigned a frequency, some kind of transaction frequency, and then they basically transact throughout the year. They live for a year and they transact at a certain frequency rate. And what we're trying to do here is basically get a sense of the transaction frequency based on this observed data. Now, we've kind of gotten rid of the lifetime problem of here, right? Because in our real world data, if you look at it, let me just go back to it. It's a good bit messier, right? Because you have different lifetimes, you have different customers being born at different times. You know, they're coming off at different times. The whole thing's a bit of a mess. So I kind of got rid of all of that, and I just went for nice, simplifying assumptions where all the customers are born at a certain time, they all live for a year, and they transact at a certain rate. And let's build a model that just recovers that transaction frequency. Now, it's a discrete frequency because it's a counting process. So it's very natural that we just use a Poisson distribution, which is what we do, which is what the PNBD model, which is the main model we're using. So the idea is that a customer is born. When they're born, they're assigned a lambda frequency for their transaction rate. So they transact over the period of year at whatever their lambda frequency is. We have decided we're using weeks as our unit of time. We could very easily use months or days or whatever is most natural. A week just seemed to be the most natural, although I could see why you would want to use a year as well. We're just going to use a week. So when we express a frequency, it's going to be a weekly frequency. And then basically we take these observations and we model them, and then we see, given that we know what the real lambda is because we generated it synthetically, does the posterior distribution for our model properly capture the known value of lambda, right? And if it does, then we know we have a reasonably well calibrated, internally consistent model, okay? And that's kind of our first step. So there is a way to do this kind of with conjugate priors. So it's a lambda frequency. So the other thing we're going to do, sorry, what I should have mentioned was the customers are randomly assigned a lambda frequency, and that the distribution for that is a gamma distribution. So we have a gamma distribution at the top that's producing a bunch of lambda frequencies, and then each customer gets their own individual lambda frequency, and then that lambda frequency is going to generate transaction counts. Okay, so that's kind of what we're looking at. And basically, the reason why the gamma and the Poisson distribution work nicely together is they're what are known as conjugate priors. So back in the day when Bayes was first considered, we didn't have high-end computations, and all these things are essentially high-dimensional integrals. So the benefit of using a conjugate prior was it meant that that integral became very, like, you could essentially calculate it by just combining the summary statistics of the prior with the summary statistics of the observed data, and you combine the two together with a formula, and then you got essentially the same functional form. So to give an example here, like if we had a gamma prior for lambda, and then we have certain observations, we can just plug those things into the gamma distribution, change the parameters, and we now have a closed form distribution for our lambda posterior. And that just makes things very nice from that point of view. So, and then, we talked about that a bit more, and conjugate priors are very common. There is a whole bunch of, there's a conjugate families where you have, the normal is the conjugate of itself. The gamma is the conjugate of the lambda of the Poisson. The gamma, I think, is its own prior as well. So a gamma with a gamma distribution has a gamma posterior. There's a whole bunch of, there's a beta and the binomial distribution. There's a bunch of conjugate priors, and typically when you're learning Bayesian statistics, you will start off with, relatively simple conjugate priors, which is what we did, just to kind of get an idea of the sense. And it means you can create nice graphs and plot things out. If you want to see more, I think it was in the second or third workshop, we talked about that a good bit more detail. Okay, so that's kind of where we got to, right? So we kind of have, our conjugate priors, but we're not going to do that. We're going to go straight in and start fitting stand models. So this was kind of the first Stan model that we fit. So we have a bunch of data. Now, the great thing about the frequency model is that it doesn't really matter. The one thing that doesn't really matter is the time between events. We don't really have to model them at all. The only thing we really have to model is the count of observed events. So what we look at is we basically see how many transactions were done during the observation window for that customer. And we use that then as a way to make inferences about the lambda. Okay. Now, the one thing to remember with buy till you die, as I said before, the customer is born with the first transaction. So we don't count that transaction as part of the frequency. That's kind of ignored. So you could have a customer with 0 transactions. What that means is the customer had 1 transaction and then never made another one. Okay, so you don't really know anything about them, but you do know that they transacted on the system, as opposed to a completely unknown customer who has never transacted at all. They are completely unknown to the system. Okay, so that's one thing to remember. So essentially what we do is we take all these transaction counts. So we just take all the data and then count the amount of transactions that occurred in that yearly period, right? In that period of 1 year, how many transactions were made? Don't forget, we subtract 1 because we get rid of the very first one. And then that's kind of our input to the model. Now, the other thing we might look at is we also look at when the customer last transacted. Because that's important in marketing. That's the recency button number they talked about. Now, we have 2 ways of looking at this. In the first case, we can kind of ignore it because we know that we have a 52-week year. However, in the real life, we don't know what the lifetime is. So we also try and model the frequency using the observed lifetime of the customer, as in up to the last transaction point. Okay, and what we're trying to do there is we know that's going to like upwardly bias our transaction inference because you're essentially shrinking the denominator. But what I wanted to do there is to get a sense for how much bias does that tend to introduce into our data. And sometimes it's good to do something that you know is wrong, just to give a sense of measuring how wrong that is. Okay, now I'm conscious I've been talking quite a bit for the last half hour. And before I get into some Stan models, I want to give people a minute or 30 seconds. Does anyone have any questions before I move on? Also give my voice a break. Okay, oh, thanks, Marion. All right, so this is our first Stan model. So like I said, we're going to pass some data into Stan. Stan is basically it's based on Hamiltonian Monte Carlo, HMC. So what it does is it basically does approximate sampling of the, it samples from the probability distribution that we then use from this. We take the sample and then we use that to basically make inferences about our posterior. It uses a bunch of kind of physics and some pretty cool numerical analysis and a whole bunch of very clever things. But the basic idea is it uses physics simulation. It treats our posterior distribution as a potential. It basically, the random element of it is the momentum. So it basically passes a particle through n-dimensional space and tracks the trajectories. And the trajectories that the particle goes through in this physics simulation is the basis of the sample that we get from our probability distribution, from our iteration. So that's kind of what it does. I probably, I'm not really doing this justice, so I don't really want to get into it in too much detail. But basically, you set the model up, it samples from it. We then have to do some sample validation, which we'll talk about a little bit later. But the idea is that the sample then is derived from physics, and it is a sample of the posterior space that we've set up, assuming that we have a valid sample, which we will talk about in a few minutes. Okay, but this is kind of how we set up our model. So we're passing in a certain amount of data that we declare. So we're saying that we have an integer, the minimum value is 1, and that's n, and that's the number of observations we've made, which is basically the number of customers we have. We then have an integer array of counts, which is basically the number of transactions that have been made on the system. We'll see that you can see that the lower value is 0. And these samples are good to prevent like bad data getting sent in and causing errors. So it's a way of kind of validating. So we should not have counts less than 0, as I mentioned before. We could have 0 though if the customer did a single transaction to be born on the system and then never did anything else. So we could have 0, but it's a positive number otherwise. And we also have a vector of weeks, which is basically how long did we observe the customer for. Now, we're going to start with 52 weeks because that was what we initially said. But the other thing, we're going to refit the model using the observed window to give us a bias sample just to see how that affects things. Okay, so that's the data that we're passing in. We only have one like parameter in our model, although actually technically it's n parameters, so it's an n-dimensional probability distribution, right? So it's just the lambda of each customer. So like I said, each customer gets their own lambda value, and that is assigned, like that's the value that we assigned when we generated the data synthetically. So that will dictate the transaction rate, and that's the lambda is the parameter that we're trying to make inferences on. So we're trying to get a sense of what transaction rate the customer is transacting at. And then this is the main part, which is the frequency, the actual statistical model. So what we're saying is that this count is a Poisson LPMF, means log probability mass function. It's a probability mass function rather than a probability density function because it's discrete observations rather than continuous. So continuous distributions are PDF, discrete distributions are PMF. And we're basically saying that we observed this BTYD count given a parameter lambda, but we've also multiplied it by the number of weeks. Because if you remember, we're scaling the frequency in terms of a weekly rate. So we need to multiply by the amount of time that the customer had to transact, okay? And that gives us, and this the target distribution, that's basically the log likelihood, okay, that we're at, and that's kind of going into the model. And then at the very end, we're calculating some generated quantities. So we're basically calculating a log likelihood, which is essentially the same value that we're assigning to a variable. So some routines, if you calculate a log likelihood like this, there's routines in Stan that give you some interesting outputs in terms of validation and loose CIV and loose CV, and there's a whole bunch of things that you can do with the log likelihood. So I thought I'd include it. So that's basically our model. Okay, that's it. So it's not particularly complicated to get started with. And what we would do at the end is every customer is assigned a value of lambda. So we run the sampler, which you can see we're running a bunch of different chains. So it's a Markov chain Monte Carlo. So the idea is what we're doing is we're creating a bunch of different chains that are starting in different parts of the parameter space. And the idea is we want the parameters all to kind of converge around a similar value. That usually is done pretty quickly because of how Hamiltonian Monte Carlo works, because it's got auto differentiation in there, and it gives you the gradients. So because you can kind of follow the gradient, you tend to go to the region of high probability mass quite quickly. But then what it tries to do then is it basically tries to explore as much of this parameter space as it can, and it does what's called adaptation. So basically it kind of tunes the parameters of the Hamiltonian Monte Carlo simulation so that it can sample as efficiently as possible. So that's kind of what warm-up is. It was called burn-in in the old days when things used Gibbs and stuff like that. And then as a result of that, we get a sampler. Is plus equal equivalent to the twiddle? Yes, I mean, it is. Effectively, this is the way they do it in Stan, because it's actually written in C++. They actually used to do it with a twiddle because of the R. But as kind of the Stan has gotten bigger and has become like multiple languages, like there's Python and there's MATLAB and there's Julia and there's a bunch, and even Command Stan. And because it's written in C++, they've started to go a bit more towards the C++ kind of type of thing. So that's just the increment. Now, plus equals doesn't actually, I don't think it works for anything else. So you can't use it like you can in C or C++. It's only there to increment the log probability. But that's basically, it would be the equivalent of twiddle that you would see in things like JAGs and bugs and stuff like that. Okay, does that answer your question? They used to have it as a function. It was increment log prob or something like that. And yes, you could go BTYD, twiddle, Poisson. I've just kind of gotten into the habit of using target plus equals because sometimes it's easier to do it that way, and it just gives you a bit more flexibility. But there's a bunch of different ways of doing it. All right, so we sampled from the distribution. We've got our samples, and you can see here we have 2001 by 10. So we have basically 2000 values. Now, the reason why we have 2000 is because we put in 10,000 customers. That's not right. What's going on here? That can't be right. Did I only fit for 10,000? I will have to check this afterwards. No, I must have done 1,000. Yeah. And so there's basically 2,000 because there's 1,000 lambdas, one for each customer. And then there's also 1,000 log likelihood values, because if you remember, we incremented the log likelihood in the generated quantities at the end as well. So that's outputted as part of the thing. Sorry, that's a typo there. I said 10,000. I should have said 1,000. Now we have some numbers, okay? But the very first thing we have to do is check that our sample is valid. So HMC and Markov chain Monte Carlo and all these aren't magic. So they basically, this is kind of one of those things where one of the problems with statistics is an awful lot, due to necessity, an awful lot of statistics are basically, certainly the way we're taught it and the way it's kind of been developed mathematically, is that you're looking for like statistical validity under asymptotic conditions. So what I mean by that is, as sample sizes go to infinity, you know, like things like the law of large numbers and you know, the central limit theorem and stuff like that, these are all valid when you have an infinite sample size, right? These things are, you know, accurate, and we can prove them mathematically. The problem is that we don't deal with an infinite world. We have a finite sample, and what we need to get a sense of is how does that finite sample differ from the infinite sample, right? And essentially what happens is there's again, I don't really want to go into too much detail. You're probably realizing quite quickly there's quite a lot going on here, but actually this is partly why statistics is so hard. In a lot of cases, these problems are real and exist in statistics, but they kind of get hidden and covered under like a bunch of default models and a bunch of default ways of doing things. And that's why people, I think, a lot of the time get quite confused or have problems trying to use these models, because like they hit up against the reality of the real world, and there's this kind of mismatch of how things work. So in this case, what we have is, while these Monte Carlo estimators work with infinite sample sizes, in reality, we only have a discrete sample. We've a finite sample, right? So we have a finite number of samples, and what we want to know is how likely is that this sample we've taken is valid. And there's a bunch of different ways we can do that. And Stan provides a bunch of them, right? But essentially what we want to make sure is what's called, the key thing for a lot of these are what's known as, it's a bit of a mouthful, it's called geometric ergodicity. So what that means is that essentially that as you take more and more samples, your parameters are kind of rotating around a flat line. So at any given point in time, when we choose a subset of the samples, they all kind of look the same. And what that means is that essentially what we're doing here, a very common thing you'll call our trace plots. So what we do is, let's say we have 1,000 iterations in our sample. We have, a sequence of samples of a parameter value, and we just plot them using the iteration number as the x-axis, and then the sample value as the y-axis. And we just plot them together. And ideally what we get is what we're seeing here, where we have essentially the different chains are all kind of exploring the same space, moving in and out a bit, and they've all kind of converged around the same thing. Now, I know this is a bit hand-wavy, and unfortunately, there are no theoretical guarantees for these things to be valid. So all we can really do, it's a bit like kind of null hypothesis testing. All we can do is do a bunch of checks, and if any of those checks are violated, we know the sample is bad, but we can never actually prove that the sample is good. However, once you've got, after a while, you get a good sense for whether or not these things are going well or not. And this is basically like a trace plot, and there's a whole bunch of kind of validity checks that you need to take. You got R hat, which is basically a measure of what's the correlation and how different are the chains amongst one another. You want it to be close to 1 and ideally less than 1.1. And you can see here we have pretty close to 1 for these. We also have a series of effective sample sizes. So basically we have, let's say we have 2,000 iterations. That's not necessarily, because these things are correlated, the effective sample size isn't necessarily 2,000. It could be less than that. It could even be greater than that if you've got anti-correlation in there. If it's negatively correlated, you can actually get more than one sample's worth of information from a sample. This is, and this is like, and there's a whole load of conversations online if people are interested in kind of the things on this. But effectively, what you want to make sure is that your trace plots are roughly horizontal, that your R hats are all kind of around 1. Set effective sample size, which is kind of related, is close to 1. And let me just put on mute. And there's a few other things we've done to check that. Once we've done all of that, and there's a few other things in there we can see, there's also, it's checking for things like tree depth. The big one here are the divergent transitions. No divergent transitions are found. So divergent transitions are typically the way in which problematic samples manifest themselves. And what is happening there with a divergent transition is, as I mentioned to you before, it's using physics simulation to simulate a trajectory of a particle through phase space. If there are issues with the posterior geometry in the way you've set up the model, what will typically happen is the numerical calculations will get problematic, and for various reasons, you'll basically rounding error and all the things that happen in, like, if any of you ever did any kind of physics in college and you had to kind of program any of these things, there's a whole load of work in numerical analysis and stuff that kind of work on these kind of things. These problems manifest themselves, and generally what happens is, if you have a bad model or you have a problematic model, that will manifest itself as a problematic geometry for the sampler to sample from, i.e. it's hard to simulate the physics, which essentially means that the simulator gets divergent transitions. So if you can think of it as, imagine the easiest way to think of it is, imagine you're simulating a satellite rotating around the sun, right? Or rotating around a planet. So you're kind of planetary motion. And if your sampler isn't great and you're not doing a good job of it, then your trajectory, which should be like either a circle or an ellipse or whatever it tends to be, will get either very, very wobbly, or sometimes will like crash in, and then suddenly, you'll head off to infinity. And it basically, the sampler itself is just nonsense because it's not correct. So what happened, that's basically a divergent transition. So your problematic model, you've done something in your model, there's all sorts of different things that can happen. We'll talk about some of them in the second hour. It's manifested itself as a numerical problem, and then that will show up as a divergent transition. And essentially you have to adopt a zero tolerance policy towards divergent transitions, because the only thing you can say about a sample with divergent transitions in it is that it's not correct. It's giving you biased samples, and this is a very real problem. So one of the reasons why Stan was developed as a tool. There was bugs and jags, which existed out there before, and they learned that there was some issues with it, with various models that they didn't realize they had problems with until they started sampling with. The classic one being the 8 schools problem, which is kind of the hello world of hierarchical modeling in the Bayesian world. We can talk about that some other time. But essentially the samples that people had for that were wrong because of these various things. And the samplers weren't looking for these issues, so therefore it didn't find them. And that kind of manifests itself. And there's ways of fixing all these things with, especially with hierarchical models. You can reparameterize your model. There's a bunch of different things you can do. Again, we will talk about all that. But essentially, that is the key thing that we need to look for. And because I've been kind of talking about Bayes for about 10 years, people often ask me for help, and they're like, what percentage of divergent transitions can I accept in my model sample? And my answer is always none. Because the problem with it is it could actually still be giving you reasonably decent answers, but you have absolutely no way of knowing, because you know that there are parts of the posterior geometry that the sampler is finding it hard to sample, and you just don't know how big that space is. You could be just exploring a very tiny part of the parameter space according to your model, and you have no way of knowing. So anyway, so that's kind of where we got to on that. So we have a bunch of samples. And what time is it? Yeah, it's 10 to 8. So we'll get ready to take a break. So now we've checked our model fit. So now we need to know, are these issues detectable in the trace plots, or don't they affect? So it depends. They can do Amin, and they usually will, but sometimes you can have models that aren't necessary. You can get decent R-hat values and still have problematic samples because you've got divergent transitions. So this is why you need to look at a few different things and make sure they're all okay. Otherwise, you can have problems. Sometimes if you have a very bad model, and boy, have I built some bad models in my time where like almost every single iteration has a divergent transition. You'll have problems all over the place, but sometimes you can have very subtle ones. And actually that will occur in some of these where we have kind of, the R-hats are a bit weird, but most of them look fine, but you can kind of tell there's a problem, especially when you look at the trace plots. So it really just depends. Okay, so before we move on, let's actually look at our data. So we have basically a model fit. So using some code, I have a customer ID, we have the draw we've done 2,000 draws in our sample, and we have our posterior lambda from that particular draw. Excuse me. And then we have what I've called customer lambda, which was when we generated this synthetic data, this is the value we assigned that customer, right? So now we have 2,000 of these values, and to compare it against this one, and that will give us then a sense of how valid our sample is. Like, are we doing a reasonably good job of capturing all the customer lambdas? And the way we're going to do that is we have 2,000 iterations in our sample, posterior sample, and we're going to compare that to the observed value of lambda, right? Now, bear in mind, this is a statistical process, so we don't necessarily expect that the distribution of lambdas to cover every single customer lambda, right? Because you could just have something that was, you could have an assigned lambda value of, 1, so they were expecting 1 transaction a week, and the customer over the period of a year transacted twice, right? So you're getting 2 over 52, right? So you get all these weird values. So in which case you would have this, very small value for lambda, but we're comparing it to the real value that's much higher, right? So the way we're going to do this is, what we're going to do is, using the 2,000 values, we're going to construct an empirical cumulative density function, right? An ECDF. So the density function, the cumulative function like that kind of like the S curve. And we're going to place the known value against the density, and that will give us a Q value. It'll give us a number between 0 and 1. This is kind of like a QQ plot idea. So we take the value, we take the known value, place it in the distribution of posterior values, and then each customer will get a Q value. And then we just look at, is that distribution of Q values uniformly distributed, okay? And ideally it will be roughly uniform. So we can see here, actually, the quantile value. So with this value, it's not exactly uniform, but it's not bad. We have this tendency to, we're definitely biased to the lower side. Now, I need to check, is that because we're doing, are we using customer weeks for this? Or are we using, I'll check that at the break. So I think I did it after though. Yeah, so I need to check on this. What might be happening here is we might be, I mentioned it before, that rather than using the 52 weeks, if we're using the shorter lifetime, as in the observed lifetime of the customer, then their lambda values will be inflated, which means the real value will be lower than that's observed, which means that the Q values will have a bias to the downside. So that's probably what's going on here. But I will check that at the break. But overall, this as a proof of concept for ways of thinking about how does this model work, because this is the problem I often have, is you have all these numbers and you're like, how the hell, especially with the problem, like we've got a distribution for every single customer. Now that's great from a knowledge point of view, but from actually trying to handle this, it can be sometimes be a bit overwhelming. It's like, how the hell do I start getting a handle on all this stuff? So that's kind of where this is kind of the method I've used, and you'll see people do this a lot for this kind of stuff. But okay, I'm very conscious. It's 5 to 8. It's probably a good place to take a break, and I'm also conscious that people will probably have questions. So what I'm going to do is we'll take a 10-minute break. It's not quite 5 to 8, but it's close enough. Let's come back at 8:05, and we'll pick this up there and then. And in the interim, if anyone has any questions, please pop them in the chat, and I will address. I'm just going to run to the bathroom quick, but I will be back in about 2 minutes. And if anyone has any questions at that period of time, just pop them into the chat and I'll address them then. Okay, I'll be back in about 2 minutes. Okay, so I'm back and unmuted. We've got another bunch of minutes, so I'm happy to just sit here and wait. Could you please explain? I'll just read out the question. Could you please explain the quantile? I thought we were going to compare the ECDF for each customer to the CDF of the posterior. So the customer only has one value though, right? The customer was assigned a single value for lambda at data generation. So it's a single value. Now, for the purposes of showing it here, I'm repeating it each time. But there's basically this number is repeated 2,000 times because it's the same value. And what we're doing is, but all these are here. It's probably easier if I show. So that's probably make more sense if I show it in the code. And thank you for the question. By all means, keep them coming. So we have a customer ID and we have a number of draws. You can see they all have the same lambda. So what we're doing is we're grouping by customer ID, and we have 2,000 values for posterior of lambda, which we use to construct an ECDF. We then put this value through the ECDF to get a Q value. So we end up with each customer gets one value, one Q value, okay? One quantile value, like Q value, let's call it. And then we plot the distribution of all those Q values. So ideally, if our posterior distributions in general are doing a good job of covering the values of the original customer lambda value, well, then we'll have roughly a uniform distribution. Does that make sense? I get it's a little bit indirect. Now, the other thing I should say is this isn't necessarily the right way to do this. This is kind of the way I've done it, right? If other people have good ideas or ideas for things they would like to see, please, by all means, let me know. I can implement them. We can talk about them the next time. This was kind of the way I've came up with. Now, of course, in reality, we have the benefit for this of we know what the true value is. In reality, we don't, right? So we don't have this benefit of capturing. But what we're trying to do is get a sense of, like, can we use this model even in ideal situations where we know the right answer? Can we recover the right answer from the data that we've produced, right? Because if we can't even do that, there's not even point in using the model any further. Okay, so I'm conscious that this is a little bit kind of what would you call it? It's a little bit. We're like I said, we're kind of marking our own homework here. But I was trying to get a sense of how does all this work. Now, it does actually raise the question, though, when we were building this, which value when we fit our model, which value for lifetime did we use for the denominator? So I should probably check that. So we've built our model. So all weeks. So that is fit. Yeah, so we're using 52 there. So what's happening there is we are still finding a certain bias in the data. So even though we're basically passing our observed window as being 52 weeks, not as being the observed time, we're still getting a certain bias in the data, which is interesting. And I'm not quite sure I understand why that is. What it might be a case of is that, so this is again what we kind of investigate. So you can see here there's a low side bias in this uniform plot. So we're seeing an overrepresentation of lower Q values rather than higher Q values. So what that means is that in an ECDF, if you can think of the ECDF as, these are the values from top to bottom. If you think of this as like the bar plot or whatever, the values are coming in lower. So our model is overestimating the frequency model, which is interesting. So I need to think about, now what it might be is that our prior is too high. So if we have a prior, because we need to set a prior for our distribution, right? So, oh no, we didn't, this is a uniform prior. Oh, that's probably what's happening actually. It's probably because we have a uniform prior. So basically, we haven't set a prior in this distribution, right? Which isn't great, but it's a place to get started. And what that means is that all values from 0 to plus infinity are equally likely, right? That's really bad. It's called a uniform prior, and it was kind of considered, the most uninformative prior. But when you think about it, that's actually not true. right? Because what's happening with an uninformed prior, actually, you know what? I should probably wait until we get back to talk about this. I think I understand what's going on there. Anyone else got any questions while we've got like another 3 or 4 minutes? I'm not sure, Greg. It depends on where I get to. I'm covering basically. I'm going to try and cover the basics. I'm not going to go too much more into the frequency model. I'm going to try and go back because there's been quite a break. So I want to kind of get back and get up to. I'd like to get as far as monetary models by the end of the hour. We'll see where we get to. Because I found the last workshop or two, excuse me, because there's quite a bit of a time gap between them. I wasn't particularly happy with how we were covering certain topics, so I just wanted to go back over everything again as a way of, making sure that we're kind of on solid ground for everything. What I think I'm going to do here is I'll talk about this. We'll talk about adding priors. We'll kind of leave it at that. We'll move on to the lifetime model. I'll cover that, and we can't really cover that in much detail because it's a bit messy, as we discussed a workshop or two ago. And then I'll introduce some monetary models, and that will kind of set us up, because my plan is to have the next workshop probably in 2 or 3 weeks' time, probably mid-August, end of August, and try and get some momentum going in for the rest of the year then, because I'm very conscious there's been like big gaps over the last few workshops, and this isn't a topic really where that's particularly useful. You're better off having a series of regular workshops for this kind of stuff, because it can get it can get a bit hairy. It's very easy to get lost in the detail. Anyone else got any questions? Okay, well, we may as well get back to it. Unless someone has it, I just noticed there's about another minute. I'll give people a chance to. By all means, there's no such thing as if you're completely lost or you don't really follow what I'm talking about. By all means, give me a shout. Happy to cover all of this. Okay, all right. So let's get back to it. All right. So we have this distribution of Q values. So as I was explaining on the break, because I got asked it again, we know a value. We know the true value that was used to generate the data for each customer, because we used it to generate the data that we're fitting the model on. So what we're trying to do now is the model gives us a posterior distribution of lambdas, and what we're trying to see is how does the real values fit into each distribution. So every customer has their own distribution for lambdas, as long with a true value. And what we're trying to do is see where does that true value lie? How well does it do? And the way to do that is we're creating a distribution of posterior values. The true value we put into it as a ECDF, which gives us a Q value. So if you can think of it like the S curve, it gives us a value from 0 to 1. 0 is basically the true value was lower than every single parameter, every single number in the posterior distribution. 1 means it was equal to or greater than every single, but most of the time it'll fall somewhere in the middle, and that gives us our Q value. And ideally what we will get is a distribution of values that's roughly uniform, because that means that generally the values are covering it properly. You know, and some values will be less than we would expect that statistically. In fact, it's probably a problem if every value is in the middle of each of the distributions, because it means that there's something weird going on in terms of we're kind of missing something, because it should be uniform, because we haven't forced anything else. Okay, now, however, as you can see here, and as we discussed, we've got this kind of bias in our model, right, where our posterior distributions are coming in high compared to the true value, right? And I checked, we were using 52 weeks, so we don't have that implicit bias of the observed lifetime of the customer. So something else is going on. And what's happening is we haven't included a prior in the model, right? We just created a uniform prior. And what a uniform prior means is basically every value allowed by the model is equally likely. And while that was originally, people were thinking of that as uninformed priors, that was what it was named, uniform priors are generally very bad. And the reason they're very bad is when you think about it, they don't really make a lot of sense. So for example, in this case here, with a uniform prior, what we're saying is that our knowledge of the transaction frequency, we're saying a frequency of 0.1 is equally likely to a frequency of 10 million billion, right? Because it's all a flat distribution. All allowable values are, so any positive number is equally likely. And we kind of know that's nonsense, right? We know that, in fact, these frequencies, these transaction frequencies, are kind of constrained. They're anywhere from 0 to, say, 10. Let's say 10 transactions a week, maybe 100, depending on the type of business we're talking about, right? But we certainly know it's not going to be 1 million transactions a week from a single customer, right? Unless we're in a very different business. So, and we just kind of know from our data that that's not true. We know kind of roughly, you know, we kind of have a sense in advance. So that's where priors come in. So I'm going to kind of skip a bunch of things there. But when we add priors to the model, we're basically saying that we kind of know in advance that, you know, there's a certain distribution of lambda values that we'd expect to see for all customers. And we plug that in as a prior, right? And there's a bunch of different priors we can put in. But now we add that to the stand model. So we have almost the same, but we're now passing in this R and alpha, which is the shape parameter and the rate parameter of our prior distribution for the gamma. So we're basically our prior for lambda, and we're passing that in as data into the model. And the reason we could hard code it if we want, but by passing it in as data, it allows us to basically build a single stand model and then pass these different prior values as data into the model, and then it will fit them, right? So it's kind of a trick. It's not technically data, it's more like variable priors, right? So again, parameters are exactly the same. We have n lambdas, one for each customer. But now we have this, and this is the twiddle that you were asking about earlier. We have lambda, which is from a gamma distribution, parameterized by R and alpha, and then the lambda is in here. So we've added the prior into this distribution now. We have the log likelihood, and we now refit our model, right? So we just refit, everything's going in. And let's just check what we've put in. So with our stand model, we're now saying we're putting in an R of 0.25 and an alpha of 1. So it's a rate, it's a shape parameter of 0.25 and an alpha of 1. And, you know, basically what it essentially means is that we have roughly a rate parameter of 1 transaction a month, 0.25, with a certain amount of variation around it, a coefficient of variation. We will talk about parameterization of the gamma distribution a little bit later, but that's basically the parameters we're putting in. We pop them both in and we get some samples, and we essentially repeat our process, and we check the posterior distribution, and we see now we get a much better uniform distribution. Okay, so you can see now it's still a slight bias to the downside, right? But you can see now that we're much more likely, like that's a much flatter distribution of values. And, you know, and that's basically because we have now kind of constrained lambda to be a more sensible set of values. So sometimes it's just worth actually plotting out these distributions, which I did here. So we can see here, like this is a distribution of lambda values for the gamma that we're using, 0.25 and 1. And you can see, you know, it's going for anywhere from 0 up to like 4, 5, or 6 transactions a week. That seems a lot more kind of reasonable as a prior. I mean, maybe we could go higher, maybe we could go lower, but certainly as a starting point, that seems, excuse me, a better way to do it. And we get a better fit. Okay. Okay, so basically that's kind of, now the other thing we can do then is we can actually build a hierarchical model. So what rather than actually set parameters for this lambda, what we would like to do is have the model actually tell us what those prior values are. So instead, we kind of create what's called a hierarchical parameter. So we don't really know what these prior numbers are. We often don't have a good sense for what the prior should be. So it's often better to, if in the Bayesian world, if you don't know the value of something, you try and put a distribution around it and then let the data kind of fit the value for it. Now, that approach does have limitations, and these limitations we're going to see. But that's basically, so if the question is, how do you set your prior? Well, in some cases you don't. Instead, what you do is your prior itself gets the parameters into the prior themselves get priors, and they're called hyperpriors. And then you can, because you can usually reason much better about them. And so, like, for example, we don't necessarily know that the average transaction rate is 0.25, let's say. However, we can say that that average value has some distribution around 0.25. And that is something we can encapsulate into our stand model and work on it there. So that's kind of what we will, so that's kind of what you call a hierarchical model. It's often more sense, it makes more sense for the gamma distribution to think about the mean and the coefficient of variation rather than the shape and the rate. Shape and the rate is the standard formulation of it, but there's a relatively easy algebraic transformation between the two. And I find personally, I can reason about the location parameter, i.e. the mean, and a coefficient of variation. The coefficient of variation, by the way, isn't like this, the standard deviation or anything. It's the standard deviation divided by the mean. So it's kind of this scaleless parameter, which gives you a sense of how much. You can kind of think of it as like it's a measure of dispersion. It's not a standard deviation, but to be honest, standard deviations don't make sense in skewed distributions like this. Standard deviations are much more useful when you have a symmetric distribution like the T distribution or the gamma or the Gaussian or any others where you've got like a nice kind of symmetry in there. In this case, because you've got a big long skew, the coefficient of variation often can give you a bit more of a sense. So basically what that means is, so let's say I have a coefficient of variation of 1, it basically means that the standard deviation divided by the mean is, the standard deviation and the mean are roughly the same value. Whereas a very high coefficient of variation means it's a much more, there's much more dispersion in the distribution. There's a much wider range of values. And we can play around with them. And, you know, that's probably something I would encourage you to do if you're, because one of the things you do when you're doing Bayesian stats a lot is sometimes you're trying to get a sense of values. So you just start plotting distributions. So I'll sometimes like literally sit down with ggplot and just start plugging in values into parameters and get a sense of the values that I'm looking for. And that's how I kind of set my priors. It's like, I kind of know the values between here and here. I'm not sure how much. I don't want anything too high because that's nonsense, but I don't want it too low either. So I want to get like a reasonable spread, and you just start plugging values in and using summary or using ggplot for a density distribution. That's plotting. I'm sorry, Greg. I'm not sure I understand what you mean.
So you are saying that you're just sitting around plotting all the variables to get your priors, the priors sorted out, right? So you're actually looking at the train data itself.
Not necessarily. No, I mean, you can do if you want, but typically what you're using is your domain knowledge. So, you know, and this is kind of why Bayes sometimes people are saying looking at the training data. You could do that, but generally what we're doing with your domain knowledge is you're more like saying, okay, I know the retail. Let's say I have some knowledge of the retail business. I know that customers, like no customer is going to transact more than say 10 times a week. Let's say that's twice a day if it's a 5-day business, right? So I don't really want my lambda to be higher than, you know, 10, right? But I also, you know, they're probably going to transact at least once a year. So I want it to be, you know, 1/52. And you just kind of play around with some parameters with the distribution of values to try and get those numbers. So it's kind of like quantile matching, if you know what I mean. You could use the trained data if you want, but quite often I don't, because I don't necessarily want to use the data yet, because I don't want to overfit my data either. It's more like what I'm trying to do is quantify my domain knowledge, if that makes sense. You know, to get where I'm coming from, and to kind of get a sense of what I expect and sometimes you will have to play with your priors to get a decent fit. Now, I have often had issues where, you know, you set bad prior values. What will happen with your priors are, if you set bad priors that don't really match the data you've observed, you'll create these divergent transitions, because what's happening is you're kind of creating two spaces that are distinct from one another, one due to the prior and one due to the data, and the sampler will have problems kind of moving between the two, and those manifest themselves as sampling problems, which means it's slower to sample. Whereas once you actually can get your priors to kind of agree with the data you've observed, now they don't have to match exactly, but as long as, you know, the space you're covering is roughly equivalent to the data that was observed, your fit will move much better. Okay, and you'll have less divergent transitions. Your sampler will sample quicker. You know, all the good stuff. Okay, so we've kind of built that, and again, we can look at that, but I don't want to go into it in too much detail because I mainly want to cover the basics here. So we did all that. We validated our models, and then we turned our attention to the lifetime models. So the lifetime, if just to go back to the start of the workshop, for those of you who weren't here before, we've kind of these vitally die models have two main aspects. The third one, monetary, kind of gets added at the end, but the main focus was the frequency and the lifetime. So what happens is, with this particular model we're working on, when the customer is born on the system, a Poisson frequency is assigned. However, the other thing that's also assigned is a lifetime. So the customer has a certain period of time that customer will transact on your website, and after that the customer will move on. Okay, and that's kind of dictated at birth, which I know is, and this is what I mean by it's quite strong assumptions. They're not necessarily true, and we kind of know they're nonsense, because, you know, a customer doesn't have a sense of how long they're going to be a customer for when they become a customer, right? Some customers will be long-term customers, and that often will change over time as well. This is making the assumption that this is all kind of set at the initial start and doesn't change, right? So again, like I said, we've got these strong assumptions, but we have to start somewhere. And I mean, to be fair, they kind of work. You know, it's, you know, and they're reasonable starting points for a lot of this stuff. So we also have, not only do we have this Poisson model, we also have the exponential distribution. So basically, the Poisson and the exponential are kind of two sides of the same coin. So when you have a Poisson distribution, the time between events are distributed by an exponential. So another way of simulating the Poisson distribution, so if you only had an exponential distribution, one way of simulating a Poisson would be to make a number of draws, keep drawing from an exponential distribution until the sum of all the draws exceeds the value that you're, like, the period of time that you're drawing for your the reference frame for the Poisson. Once it exceeds that, then the number of draws that add up to less than or equal to the reference frame is your draw from your Poisson. So they're parameterized the same. They both have this lambda frequency. It's in this case we call it what did we call it in this model actually? Hold on, we called it something else. Sorry, I'm blanking here. It was lambda and epsilon. No, it's not epsilon. What the hell is it? Mu. Sorry, Jesus, I completely brain freeze there. So we had a lambda for our Poisson distribution, and from that we're realizing discrete counts. With our exponential distribution, we have a similar parameter. Now we're calling it mu, But the realization of this is continuous values, positive numbers, right? And they are the time between events. So that's actually what we used to simulate the data, right? We didn't actually use a Poisson because we needed the actual timestamps of the transactions. So what we did was we went, you know, for the data we started, we would draw from an exponential. Is the draw for a given value of mu, or for a given value of lambda, is that value less than like 52? Yes, keep drawing, and you keep drawing until the sum of all those numbers is greater than 52. And then we take all the transactions that are within 52 weeks, right? So that was kind of how we did it. So we're going to do something similar here, but now we're going to use it for the lifetime, right? So what happens is at birth, okay, according to this model, we have a customer is assigned two numbers. It's given a lambda for the frequency rate, and it's given a mu for the lifetime, right? And then we draw from the frequency, and you know, that's the transactions, but or we could use the exponential if we actually want the timestamps, right? And for the lifetime, we just draw from that exponential distribution using that mu as a parameter, right? And that gives us our lifetime value. So that's how long the customer is going to be alive on the system, okay? So now, and then and that's what we're going to use, right? So, and then with the combined model, which is the Pareto negative binomial distribution model that is used, you kind of combine the two together, right? So you have both the frequency and the lifetime kind of interacting with one another, because obviously the Poisson model requires knowledge of the lifetime, and the lifetime also needs the knowledge of the Poisson, right? Because if you have this very high Poisson rate and suddenly the person stops transacting, well, it's becoming more and more likely that the customer has died, right? And is no longer transacting. So the two of them kind of interact that way, but we'll get to that next week probably, or next month. So the problem with the lifetime model though is that we don't have an observation. Unlike we can actually see the transactions occurring, we can't actually see the lifetime. All we know is what the minimum value of the lifetime was, as in we know when the customer last transacted, but we don't know anything beyond that. So we have this kind of censored observation. Now we can still handle that in Stan. So what we do here is we can say that basically there's a minimum lifetime. So we say the customer was born at this point, and then, you know, like the last transaction happened after 45 weeks. So therefore, we know that the lifetime of the customer is at least 45, right? And we try and use that. Now, as you can imagine, it's censored data. So we're using the cumulative, the ECDF, and we're fitting on this. But we also know that it's the complementary one, because the ECDF goes thing, whereas we're trying to go, it's the highest number. So it's 1 minus the ECDF, if you see what I mean. It's like a survival curve. And that's the LCCDF. And again, minimum lifetime and mu. We also have a maximum lifetime, which I kind of included in there, but was probably a mistake, to be honest, because the minimum lifetime proved to be, the maximum lifetime was so big, it didn't really tell us anything at all. I included it in there, but it doesn't really add anything. In fact, now that I'm thinking about it, I might even get rid of it because it just didn't add anything. I was kind of hoping that if we had like, and by the maximum lifetime, we say that we know that no customer is going to last more than, say, 10 years, right? At least in terms of our observation, or 50 years or whatever it's going to be. But the point is that it ends up being so ridiculous, it doesn't actually give you any resolving value. So we try and fit this model. Okay, so we have these minimum lifetimes, and we're trying to fit this with this survival curve. But again, we don't expect this model to be very good, because we're trying to get a parameter. It's a single distribution, which is the exponential, but we don't really have observations of the distribution, right? All we have are these censored observations, kind of like you do if anyone has ever done survival analysis. So we expect these values to be quite noisy. And sure enough, when we actually try it first, the whole thing explodes, right? We end up with Where is that? It should be in one of these. Because we forgot to include a prior. So again, essentially, because and this is why priors are important for this kind of thing, because the values are very, very high, and all these high values could be included. So we don't really get any resolution power. Yeah, I remember I meant to check this. There's something weird going on here because sometimes they fall over, and you can see like but those numbers seem okay, which is very weird. All right, I need to check this again. I was getting divergent transitions when I ran this before, and now they seem to have gone away, which is weird and makes me unhappy because it should be good and I should forget about it and go away. It works, but it's not expected behavior, and that always makes me a bit scared about my models. So I'm going to check that after we're done. But instead, what we're going to do is we're going to add a prior. So now what we're saying is we know what the minimum number is, but we kind of have a rough sense for how long customers are lasting, right? So like, what's the average lifetime of a customer on the website between first transaction and last transaction? You know, how long would we expect them to last? Maybe a year. So if it was a year, that would basically, you can think of it as the exponential as the dropout rate. So if we expect a customer to last, say 52 weeks, well then the mu value is 1/52 because it's stated like a Poisson. Okay, and basically we get divergent transitions, but once we add the priors, they go away, but we end up with pretty bad samples, and that's our QQ plot. So you can see basically that, you know, what's happening here is we're estimating a lifetime value here, and the true value is much, much higher. So, you know, we're basically, the problem with these models is because they're so censored, because we don't really have any resolution in the model. Every single value that we're trying to get, we're trying to resolve we don't even have a true observation of the lifetime. We only have a minimum value. So basically what happens is we just end up with an awful lot of statistical noise and not a lot of statistical resolving power to actually be able to say anything clever about the resolution. So we tried a bunch of things, and we talked about this previously. These are all absolutely terrible. My plan was to actually do more on these, but the model is so terrible, there's not an awful lot of point beyond here's what happens when your model sucks kind of things. So what we're going to need to do to get a better thing is we kind of need the two together, right? So this is where the PNBD model comes in. Now, I should point out there is a completely different model. Well, not completely different, but there is an alternative buy till you die model, which is called the BGNBD model. So the beta geometric negative binomial distribution. So that takes a different approach, and that's something we'll probably talk about in a couple of weeks' time. It works under a different set of assumptions. So it's the exact same on the frequency side. It has a gamma distribution that leads into a Poisson, which is the negative binomial distribution, by the way. For those of you who've ever used a negative binomial, that's another way of generating one. You sample from a gamma to give you your lambda, and then you sample from the Poisson, and that's how you get your over dispersion. However, on the lifetime side, it takes a different approach. So what it does is, it rather than assign a lifetime at customer birth, instead what it says is that at every point of transaction, the customer has a fixed probability of lapsing or dying, right? So basically, instead of saying that this customer is going to last for 52 weeks or whatever, instead what we say is every time a customer transacts, the customer may lapse. And there's a 1% chance of a customer lapsing after every transaction, right? And that's how you model your lifetime that way. So rather than have an explicit lifetime model, it's more like tied into the Poisson rate. And one of the that is the benefit of the BGNBD model is it's a much simpler model to fit, because you don't have these nasty kind of unobserved values for your lifetime model that are kind of hard to resolve. Instead, what you're saying is that there's a fixed probability, and if the customer stops transacting, then finally that binomial trial came up positive. Okay, the Bernoulli trial came up positive. Okay, And those are much easier to fit. Apparently, one of the big benefits for why they were done is because you could write them in Excel and they modeled. However, the problem with the BGNBD is that they have a tendency to underestimate the lifetime of customers that transact very frequently, which makes sense when you think about it, because the customer who is transacting more frequently, if you, let's say you have two customers, right, who have the exact same probability, like let's say 1% or 10% probability of dying, right, at transaction. If a customer is transacting more frequently, they're getting more opportunities to lapse, whereas a less frequent customer has less opportunities just because there's less trials being taken. So the lifetimes of the probabilities of a customer still being alive on the system is much lower for higher transactions. And it's a known kind of issue with the BGNBD. However, I do know a bunch of people who have used the BGNBD models very successfully in their work. And in fact, the person who first got me onto these models was mainly using the beta geometric negative binomial and was very, very happy with it. And like I said, it's much easier to fit. And I think the reason, I mean, this is the other thing, there's all sorts of reasons were given for why the PNBD has problems fitting. And I think it goes back to the Stan thing I mentioned before of these divergent transitions. The problem is, in many cases, that your model and your data aren't meshing well enough. And whenever I hear of these problematic fitting, I usually think the problem is with the model, right? So you need to re-specify your model. You need to do something different. Maybe narrow your priors, maybe reparameterize your model, do a whole bunch of different things to that. Okay. Okay, so it's about 8:30. So I'm going to, so that's kind of a quick, now it was kind of a whistle stop tour, but I wanted to kind of cover at least at a very high level, focusing more on the frequency because it's easier to get a grasp on. And also just the lifetime model isn't great on the PNBD model. So what I want to talk about briefly now is the monetary models. Okay, but before I do that, does anyone have any questions about everything I've said? Because I'm very conscious the last half hour was very much a whistle stop tour of everything. Let me just grab a drink while I'll give people the opportunity to ask a question. Okay. All right, so we're now going to ignore the BTYD, the buy till you die models for the moment. We're not ignoring them, we're just going to put them to one side because the next step for all of this is to combine them together and try and get some sense out of them and see if we can combine the two together, and they'll give us essentially what we would like to have is a parameter for the lambda and a parameter for mu. So then we can start discriminating between customers who have like high transaction frequency but low lifetime, low transaction frequency, high lifetime, and so on, and you know, create some stuff around that. But the other key thing as well that these models don't represent, and this is what we're going to move on to now, is the monetary aspect of it. So what we also want to do is not just model how often, for how much a customer transacts, how often, and for how long. We also want to get a sense of how much money they're spending. Okay, so the model for this is shock horror, a gamma gamma, right? So we have essentially what we're doing is that every customer transaction is a draw from a gamma distribution, right? And then there's a kind of a customer population effect with another gamma distribution. Okay, so essentially there's three parameters set in this. So we have a gamma distribution, we have a customer parameter that's P, right? That's a fixed number. And then we have a gamma distribution that creates the second parameter going into the gamma. And then those two values together are put into a gamma distribution. And that gives us the value of our transaction amount. So at the very high level, for any individual customer, there's a gamma distribution that dictates all the monetary values for that particular customer. But then there's a population effect with this kind of hierarchical gamma as well. So there's three parameters, P, Q, and gamma, small gamma. and the Q and the gamma go into, or let's call it G. All right, so you P, Q, and G. So Q and G go into a gamma distribution and give us a value nu, like Greek letter nu, and then P and U together are drawn. We run them through a gamma distribution, and that gives us our transaction amount. So we have a bunch of customers here, and then we have, where is it here? Yeah, so we have all the data here. So we have a customer ID. This is from our simple data set, and we have a transaction timestamp, and then we have the transaction amount. All right, so that's just visualization. This is some data that this is the real data that we plotted. We're going to fit some transaction amounts, and basically this is kind of, you can see the distribution here. So we have P and U, and the nu is drawn from these parameters Q and G. G is the little gamma in the distribution, and that gives us our transaction amount, right? And so therefore, for we have this customer with this P, and we have P here. I don't like reasoning in terms of shape and rate, even though that's the natural parameterization for the gamma distribution. I much prefer to think in terms of location and coefficient of variation. So what I tend to do is set my priors in terms of the coefficient of variation and the mean, and then do this calculation to give us our values later on. I'm actually going to do a better one. I just didn't get a chance to do it for this workshop. When we come back to it, probably in a couple of weeks' time, I'm actually going to, P, Q, and G are kind of in shape and rate terms. What I want to do is create parameters in terms of mean and coefficient of variation terms. Okay, and when I do that, I think that, because in terms of setting your priors and in terms of reasoning about things, it's a much easier way to think about things. So you can kind of do them directly in terms of your distributions, and then have Stan do the coordinate transformation for you. And Stan kind of, as long as you're kind of doing it correctly in Stan, it allows for all the kind of the Jacobians and all those kind of things that you need to account for. Okay, right. So basically, it's the exact same thing. So we have these three parameters. We have a P, a Q, and a G that we're going to pass in as a parameter. We have some values that we're going to sample through, and then at the end we end up with a nu for every customer, which is the rate parameter of the gamma distribution, right? And we're going to plot all that, and then we do the exact same thing. Do we have, is it viable, or is it a valid sample? The R-hats look good, the trace plots look okay, sample sizes, yeah, they're all pretty reasonable. You can do some coordinates. And actually, in terms of the Q values, so again, we have this customer nu value, which is a Greek letter nu, that we've determined for every single customer. And then our posterior is drawing a customer nu as well. And we're checking to see, does this look correct? And actually, that's a pretty decent uniform distribution. You would always kind of expect the zeros and the ones to be a little bit underrepresented. That's just kind of standard for this sampling, I've found. I think it's also got to kind of the way the histograms tend to work, because they're kind of centered in the middle. So you kind of have that kind of values, and you've got a hard limit at 0 and 1. So because you don't have that kind of bleed over the edge, it's sometimes the very, very extreme values just kind of get squished a bit. But in general, the model fits quite well. So you can see in all the various, so this is another plot of the customer P against the quantile. So basically, every customer, the real value. So is there a trend? Like, are we finding that low values of customer value, do they tend to, is there a relationship between the Q value we're observing and the actual value that that we're putting into the ECDF? Because that might show values. For example, if we're finding that particularly high values of the parameter tend to have low Q values, or high Q values, it's telling us that there's some kind of bias in the data set that we found that we need to, that we can address. But actually, in general, this is actually behaving quite well. So even though we have, again, we're marking our own homework here, we've kind of used these values to produce the data. to produce these transaction amounts, and then we're trying to use that model to refit it, it's actually not doing a bad job. So at least in terms of the frequency model is doing a decent job, and the monetary model is doing a decent job. We're doing okay. Sorry, I see a question here. I was wondering if we could see the match for these models somewhere, maybe in your blogs. So I mentioned it above in some of the stuff. The best for it is if you go, there is a package in R called BTYD, and there's also another one called CLV tools, and they have a couple of vignettes and a couple of functions where there's fairly decent papers on this and in the documentation. Also, if you look on the Peter Fader website, for this, it's called the Gamma Gamma model for transactions. And if you want to just Google BTYD and PNBD, they're all over the place. Hold on, let me just put all them in here. So I'll type it in here. So hold on a sec, everyone. So BTYD models, in particular, PNB. Peter Fader has a whole bunch of journal articles. They're available off his website, and I think there's a bunch of references in both CLV tools on CRAN and BTYD on CRAN. There's the vignettes has a bunch of academic links, and I think there's URLs for them as well. I could be wrong about that. That talks about the maths behind it. In particular, for the monetary models, though, you want to look at the gamma model. Now, the thing I don't like about the gamma though, and again, this is I'm evolving as I go. I don't like the way the parameterization. First of all, I don't really like the way the parameterization is done. I think I'd do it differently. But secondly, to me, a more natural way to do it would be to have basically a fixed population distribution, right? So every customer has an average value that's determined by a gamma. So the hierarchical gamma determines the mean for each customer, and then each customer has an additional value for the coefficient of variation. So that's how, if I was to split it up into 3 parameters, that's probably how I do it. And then I would just do the maths to figure it all out in terms of how I turn that into from a mean and a coefficient of variation into a shape and a rate. Okay, because I can think about that much better than I can in terms of shape parameters and rate parameters for a gamma distribution. Okay, so that's probably a good place to leave it. So I've kind of summarized the 3 main components that we're looking at on an individual basis, and I've used kind of toy data synthesizing methods for this. So what we're going to do next week, or in a couple of weeks' time at the next workshop, is we're going to start looking at the PNBD model. So again, I'm going to use synthetic data to start with, and then quickly move to real data, because it's now time to start actually working in the real world where real problems appear, because it's all very nice to have that. But one of the problems you're going to find is that you can't actually give these models too many degrees of freedom. You actually kind of have to either not have, you kind of have to set actual values for priors, because if you put too much, if you start putting hyper priors on things, the data can't actually resolve these values, and you get divergent transitions, and you get poor mixing, and the Bayesian fraction of missing information. You get basically problems with your models. And what's happening is that there's degeneracy. So the model has actually too many degrees of freedom, and it's not able to properly, you've got identifiability issues. So the way to solve them is to constrain the model, right? So if you don't put any parameters, if you just set your priors with actual individual values, the models fit okay. But I find that very unsatisfying. Like, kind of, what's the point? The whole point of these is that you don't necessarily know what these numbers are, and you want the data to tell you as much as possible. So what I found is that you can kind of add certain degrees of freedom, but not too many. and then your models fit okay. And that's what we're going to kind of talk about in the next workshop. When exactly it's going to be, I'm not sure. My gut feeling is probably in 2 or 3 weeks' time. I'm going to tentatively say August the 22nd, but I will probably decide in the next few days, and I'll put something up on Meetup. But other than that, I'm going to leave it there in terms of the content. I'm going to hang around for another 10 or 15 minutes if anyone has any questions. But other than that, thank you everyone for coming. I hope I didn't confuse everyone completely like I did in the last month. Like I said, hopefully you're all starting to realize why I didn't want to cover these models last year in the soup to nuts, because there's quite a lot going on with these models. And I found problems fitting them, which is what made me think in terms of doing them in Bayesian, because the other great benefit of the Bayesian approach is it actually helps you diagnose. It gives you a bunch of tools for diagnosing these problematic fits and allows you to do something about it. And then even if you want to switch over into the maximum likelihood world, well, at least you've kind of figured out where the problems are. But other than that, hopefully that was helpful to people. Like I said, I'm going to hang around for 10, 15 minutes. I'm booked in until 9. I'll happily stay on if people have any questions. But if other than that, by all means, enjoy the hour or two left of the bank holiday, and hopefully I'll see you soon at the next workshop or the next Dublin Data Science in-person meetup, which will be in September. So other than that, thank you very much, and hopefully I'll see you all in a few weeks' time.
Hi, Mick. Can I ask you a quick question?
Of course you can, yes.
First of all, thank you very much for this talk. It was great.
No problem.
My question is more general, not a specific to this model. I'm mostly used to JAGs, and I'm starting to practice with Stan.
Okay.
One thing that I found it difficult is that people mostly refer to the documentation of a Stan as a good reference to start learning it. But to me, vignettes are better, like having real examples and seeing math and how actually it's done in a Stan. I was wondering if you could introduce some references or sources you think would be useful for me to learn a Stan.
Coming from a JAGs and bugs background?
Yes.
Right. So I presume you've got John Krushke's book?
Could you put his name in the chat?
Yeah, of course, John Krushke. He had the original. It's like doing Bayesian analysis using JAGs or bugs, whatever it was. He had first edition. In the second edition, he started using Stan. Now, I actually prefer a book called Statistical Rethinking by Richard McElreath.
Yes, yeah, I know that one.
Yeah, and he is kind of using Stan in a bit of a weird way, I admit. There's also an excellent book by Andrew Gelman, who's kind of the main academic kind of figurehead of Stan. It's called Regression and Other Stories.
I see.
It came out about a year ago. It doesn't necessarily assume JAGs or bugs knowledge, but it's all based in Stan. It's very good. The Stan documentation itself, there's 3 or 4 different documents now. There's a reference manual and a function reference. There's also a user guide. The user guide is quite good and quite accessible, and kind of has a lot of kind of hand-holding in it. So I can definitely recommend that as well. It's hold on, you can see my screen still. So I think it's called the user guide. I found that's pretty well written, I found, and is kind of based around, it's not a function reference. It's talking about, the ways in which things are done, and talks about how to use Stan, and has fairly high level bits. The other thing, and they talk about different techniques, and especially towards the end. So that stuff can be quite handy. Also, there is a Stan discourse on Discourse. I think it's discourse.org. Discourse.mc-stan. Hold on. You can see my screen, can't you still?
Yeah, I can.
I think it's discourse Stan. Yeah, the Stan forums. There's a lot of very good stuff on there that I really like. The other one is there's a package called BRMS and RStanArm that if you know how to use R, it basically creates a Stan interface to standard like statistical modeling, like GLM and LM and a bunch of things like that. And BRMS as well has some pretty high level ways of just getting started. So like if you want to fit a GLM in Stan, it lets you do that in a fairly straightforward way and handles a lot of the plumbing for you. Let me think. Is there anything specific you struggle with?
Yeah, once I tried using BRMS, but for me, for example, in JAGs, I can easily deal with missing values. I can put distribution type on them, and JAGs takes care of it easily.
Yeah.
I don't know how to do that in
so
BRMS.
there are certain things you can do in JAGs that you cannot do in Stan, and that is very deliberate. So one example is you cannot have discrete parameters in Stan, whereas you can in JAGs. And the reason for that is the one thing that Stan is big on, much more so than a lot of the other probabilistic programming language, is statistical validity. So no one knows how to actually check that samples are valid with discrete parameterization, because you don't have this continuous sample space to do your trajectories that are inherent in HMC. So it was one of the things that got asked a lot, and they basically say, we don't do it. We will do it as soon as people figure out how to do it in a way that means that we can actually stand over our answers. Because the problem with a lot of these models, you can handle missing values in Stan, and there is a chapter in the Stan user guide that discusses that. But it is, you kind of have to, you can handle discrete parameters as well, but you have to marginalize them out. So you cannot have discrete parameters. So you can have models that have discrete parameters in them, but they have to be marginalized out for the posterior. So you kind of have to do something in your model to remove those from it. So there's a bunch of different ways in which that gets done. They talk about that quite a bit in the Stan user guide as well.
I see. Thank you very much. Okay.
No, but by all means, drop me a mail. I mean, my email is on this, mickcooney@gmail.com. If you have any other questions or you're having struggles, it is possible though that what you're trying to do in Stan isn't possible by design, because of that lack of statistical validity, which is it's kind of what the Stan guys, it's how they stand out from the crowd. That's what they're saying. They're okay to not be at the cutting edge of some of the things like, TensorFlow probability and that other one. There's a new one that's been used for like approximate. It's why they don't really do variational inference as well, because there's no real way of checking if your variational inference works. There is a few people who are big into Laplace approximation though. So there has been talk of implementing Laplace approximation inside of Stan, because there is some kind of tie-in with the INLA guys that are based out of, I think it's Norway. Or maybe it's Finland. Sorry?
Havard Drew, I guess. His name is Havard Drew.
He's one of them. There's another guy though. What's his name? Havard Drew is one of them. There's someone else who's kind of on the Stan forums a fair bit. Aki Vatari.
Aki Vatari,
yeah. I think he's involved. He looks at some of that, but I don't know if. And then another guy called, I think his name is Dan Carpenter. He's an Australian guy. He writes absolutely hilarious blog articles on the Andrew Gelman blog, although he hasn't for a while. So yeah, there is stuff, but it's possible what you're trying to do isn't directly translatable into Stan. Now you could still do it, you just might not be able to do it the way you were doing it in JAGs.
I see. And one more question. I was wondering if you came across the PyMC.
Yes. Yeah, and it's actually gone to 4. So PyMC 4 uses the same underlying technology in the statistical stuff.
Yeah.
So they use HMC and a bunch of other. I think they use nuts, although it's not really nuts anymore in Stan. It's something else that they've kind of expanded upon. But they also they do a lot more variation on inference and stuff like that as well. PyMC 4 is meant to be very good. I've only ever really looked at PyMC 3 and not in quite some time. But yeah, it's supposed to be really good. Chris Fonnesbeck is no fool. He knows what he's doing.
Great. Thank you very much.
If you're into Python as well, though, there is now, and you want to stick with Stan, there is a lot more support for Python in Stan. There wasn't before because a lot of the stuff was PyMC 4 and PyMC 3. But there is a whole bunch of, like the Aki Vitari, there's a whole bunch of people now that are heavily involved in Stan that are also Python guys. So there's a bunch of Python libraries now that are part of the Python, the Stan ecosystem.
I mainly want to move on from JAGs because of the computational stuff that I'm dealing with. I'm dealing with time series with a lot of observations, and JAGs cannot deal with them very well. So that's why I'm really looking for a sampler that is fast and also reliable.
Yeah, so now the one thing to say is they can be competing requirements. So something that's reliable, if you have a lot of data points, Stan is going to be, it'll probably be faster than JAGs, but it might not. Again, it depends on what you're trying to do. The way they talk about it, they don't look so much as computation time because you're not really drawing comparisons. So the way a lot of these are looking at are called effective sample size per second.
Yeah. Because
one of the problems with JAGs is you can have like 500,000 samples, but actually most of them, you only have, a couple of hundred effective sample size. Whereas that's why Stan iterations are much shorter. You generally don't draw more than 2 or 3 or 4,000 iterations in any given sample. That's actually more than enough for almost all work because usually the ESS is quite high. So that's the other thing to look at when switching from Stan to JAGs. If you're in JAGs, you might be used to doing like 100,000 samples and thinning. You generally don't thin in Stan, and you generally only go for like 4 or 8 chains with maybe 1,000 iterations or 500 iterations in each sample.
Yeah, that's true. Great, thank you very much.
Cool, no problem. Thank you, Armin. Thanks for joining in. Hope to see you again. Okay, anyone else got any questions before I go? No? Okay, well, thank you very much. I'm going to leave it there. Like I said, I'm expecting to do the next one around the 22nd. It'll just depend on how things go over the next couple of weeks. But other than that, thank you everyone for coming, and I hope to see you all again soon. I will turn off the recording.